Welcome to this video on the electrochemistry topic. Our subject today is cell reactions, and we want to know what chemical changes take place at each electrode in a cell when we allow the current to flow, and we want to be able to construct an equation for the overall reaction taking place in a given cell. So let's begin. We'll start by looking back again at the zinc-copper cell that we've used frequently in previous videos. If you're interested in working out the cell potential for this, please see a previous video. You can click the link now. So we found out in the last video that what we've got here is that copper is more positive than zinc. And what that means is essentially that there's going to be more electrons deposited on the zinc than there is on the copper. And if we put a high resistance voltmeter in here, it allows us to essentially take a photo, a snapshot of this potential difference, which we call the cell EMF. Now what we're going to do is allow current to flow. We're going to change the voltmeter for some normal component, be it a bulb or any other type of circuit, and that's going to mean that current can now flow. So the question is, which direction is current going to flow in? Well, it's going to flow from positive to negative, and that means the electrons are going to move from negative to positive. They're going to move from an area where they're very concentrated, a high negative potential, to a more positive potential. So the electrons are going to move down the wire in that direction, and these electrons will move out into the wire here, and there'll be some other electrons down here that will move and reside on this piece of copper metal. So when we allow that to happen, we're going to see that there's going to be more electrons on this piece of copper metal. So what we've done is we've actually disturbed our equilibrium on this side. We've increased the concentration of electrons on the piece of copper. So what's the effect that that's going to have? Well, by Le Chatelier's principle, if we've increased the concentration of copper, the equilibrium system responds to minimize that change, and the equilibrium will shift to the right. Equilibrium shifts right. In other words, a copper 2+ ion is going to react with a couple of electrons and become a piece of copper metal. What about on the zinc electrode now? Well, the electron concentration here has gone down because our two electrons that were here have now gone over onto the other side. Well, actually they've become part of the wire, and other electrons have moved from the wire onto the other side. But those electrons are gone, so the electron concentration is down. And again, using Le Chatelier, we would predict that the system responds to minimize the change. In other words, the equilibrium shifts to the left. So in other words, a piece of zinc from here is going to lose a couple of electrons, deposit those back on the remaining piece of zinc here, and another zinc 2+ ion will form. So that's what this slide shows here. Extra copper formed and zinc 2+ formed. So now in this position we've got 2 electrons back on zinc, and we've taken up 2 electrons from the copper electrode. So the potential difference is now restored, and so the same thing will happen again. The electrons will just move along here, and then the cycle will continue. So more copper 2+ will collect a couple of new electrons, a bit more zinc will react, releasing more electrons, and so forth. And the process will carry on all the way until you've either used up all your zinc, it's become zinc 2+, or you've used up all your copper 2+ ions. And here I've just shown that the zinc has now broken electrical contact. And that's essentially what happens when your battery runs flat. So what's the actual overall reaction that's happened here then, the cell reaction, when we've allowed current to flow? Well, we've said that essentially what's happening here is the copper 2+ ions are gaining electrons to form copper, so essentially the forward reaction happens here, and the reverse reaction is happening here. So if we put those together, what are we going to get? Well, we're going to have zinc solid, and that's going to react with copper 2+. Now these reactions are happening in completely separate compartments in this cell, but they're nevertheless essentially reacting together, and that's going to form zinc 2+, aqueous, and copper metal. Here's another example. So cells constructed using the following half cells. What is the cell reaction? So pause the video now and see if you can work this out. Okay, so the first stage to this is to decide on which is going to be the positive half cell. So in which case this one is going to be positive and this one's going to be negative. And we said last time that the positive half cell, the electrons are going to be gained, so we're going to have reduction here. So this reaction is going to move in the forward direction. Whereas this reaction, we're going to get oxidation, because we're going to get loss of electrons. Those excess electrons are going to go, and so we're going to get the reverse reaction. Reverse reaction is going to occur. So if we write those out, then we're going to see Sn, I'll just leave out the state symbols for clarity, is going to become Sn2 plus 2 electrons, and in this case the manganate is going to react to form manganese dioxide and some hydroxide ions. And at the moment this one was requiring 3 electrons. Now in order to be able to combine these half equations, we need to make sure we've got the same number of electrons in each, and so if we multiply the first equation by 3 and second equation by 2, we can essentially get 3 tins, 3 tin 2 plus 6 electrons here, 2 manganates, 4 waters, 2 manganese dioxides, and 8 hydroxides. So if we then add our 2 half equations together, we're going to add these 2 equations together, then we're going to end up with the following full equation. 3 tins, 2 manganates, 4 water, 3 tin 2 plus, 2 manganese dioxide, and 8 hydroxide ions. We just quickly check that everything is balanced. It should be balanced for atoms, so 3 tins, 2 manganese, 8 oxygens, and another 4 makes 12. And here we've got 4 and 8 making 12, 8 hydrogens and 8 hydrogens, and we just check the charge is balanced. This side is going to be a 2 minus charge, this one is 6 plus, 8 minus, 2 minus, so the charge is balanced. So this is the correct equation. Let's summarize then what actually happens at the electrodes in a cell. So at the positive electrode, we've got the more positive standard electrode potential, and at the negative we've got the more negative. What that means, the more positive means that the redox equilibrium is further to the right, so we have a stronger oxidizing agent here. So the equilibrium further to the right. And here we've got a weaker oxidizing agent. The net, so this is the equilibrium further to the left. The net result of that is the stronger oxidizing agent will essentially oxidize the species at the negative electrode, so this is going to be oxidation taking place, which is loss of electrons, and reduction is going to happen The positive electrode, an oxidizing agent, is something which is easily reduced, and electrons are gained at that electrode.